Okay, forward.
So so without any delay, now let me start. I'll be talking about quantum simulation, quantum sensing with trapped ultracold atoms, and I work on theory. So what I thought yesterday that each of my work involves a huge amount of calculations, and so I thought that thinking of uh, the type of audience that maybe majority is experimentalist. So I refrained myself from putting calculations in the slide unless it is really required. But I took that advantage for putting more number of works so that I can give an overview of what is going on in my group. So let me go ahead. So this is the perimeter of each of these directions. So I'll start with a brief introduction to the way we actually address quantum simulation part for trapped BEC. And then I'll mention about how we actually have kind of a stable structure, solitonic interaction in the bichromatic lattice and four-color lattice. Then the new directions which Professor Osgur also mentioned about negative absolute temperature. The first experiment was done for ultracold atoms. So a model, exact model of it, and then trap engineering. And this application is about predicting this phenomenon for the first time in BEC, which is fractional removals. Okay, and which actually brings in a lot of applications in quantum information science. Then I'll be ending with a few glimpses of quantum sensing applications in BEC in a trap. So I'll also start with the quote from Feynman. So because this was the starting point of quantum simulation, he mentioned is a remarkable intuitions by saying that the systems which are controllable and can be manipulated easily and stable, that can simulate other systems. So that was quite remarkable. But then recently, this I'll start with some kind of a proposal that this is one of our works in 2015 is a quantum optics work where we have seen the mesoscopic superposition of generalized coherent states and the superposition structure in between for a different set of rings in phase space. Okay, and then this is the kind of structure we get in the middle, which actually mimic Bessel function. And so what I think that this is a picture taken from science paper, a STM picture of arrays of copper atoms. So if you look at the center of the system, then this interference structure is never analyzed properly. So I guess that this structure will be kind of similar to this, and one can actually look for with this kind of thing. So a quantum optical system can be looked at. In this work, actually, we have connected this interference pattern with the diffraction, so classical optical situation to a quantum optical situation, but this can be taken to a condensed matter scenario. So this is one way that I am just thinking, we have not mentioned in the paper, but it is open if somebody interested can go ahead with this kind of thought. So mainly, I'll be talking about ultracold atoms. So when I talk about ultracold atoms, that how to go ahead. So I'll start with just mentioning about the discoveries, because these are very important landmarks in physics. That when S.N. Bose discovered and derived Planck's blackbody radiation formula, it was a kind of foundation of quantum statistics field. And then Einstein modified it for massive particles by giving it as a Ghosh-Einstein distributions. And that was the discovery for the distributions at low temperature, ultra low temperature, can give you a physical situation where you can trap bosons, a large number of bosons in a single quantum state, and which is called a Boshinstein condensation. So it took 70 years in the experiment. In 1995, they did. Cornell and Neumann did it in June, July, and the month, and Kettle did it in September. In the same year for sodium atom, and which actually attracted Nobel Prize in 2001. So the salient features which I wanted to mention for going ahead is these 3 points, However, I'll go in this direction. So first I'll mention about this thing, the condensate is purely of quantum origin. That you have to remember. And then this is a highly tunable object because it's a laser mediated process. So you can control the laser and magnetic fields to do a lot of tuning and engineering in the system. And fortunately, it has a very long coherence time. So it's a coherent state of matter, I can say. And but there is one thing that it occurs in momentum space because of the ultra low temperature, your momentum is very small. So it is almost kind of localized in momentum space, not in coordinate space. So from here it starts the concept of trapping in BEC, that if you have no control in coordinate space from the uncertainty principle, that if it is completely localized in momentum, it should be delocalized in position, right? So if it is real space, it is delocalized, then we cannot have technologies in it. So you have to have a trapping, useful trapping for this to use it for further. So that is the idea. So we'll be definitely using BEC in a trap. But first of all, this trap, what kind of trap will be appropriate for quantum simulation? So the most appropriate one I'll be discussing, but before that, as I said, I will not put mathematics for each and every works, but then I'll give you the general approach which one should go ahead, and it took very long time for us to crack this kind of solutions. There is no exact methods of bichromatic lattice and beyond. Even optical lattice, there are very typical cases periodic solutions. Bichromatic lattice, there is no solution in literature so far. So what we do is look at this equation, which is the nonlinear differential equation, nonlinear Schrodinger equation. You have a dispersion term, you have external potential here, you have nonlinearity, which is all of you know that because there are a number of talks have gone through in this direction. So this is coming from atom-atom interactions. So mainly is a two-body interactions we are considering here, without considering the higher power of this two-body interaction as a loss gain term in general. So now all these coefficients are space and time dependent, and it is extremely difficult to handle this because of two things, that you have a nonlinearity term here with is a cubic nonlinearity here, and also in presence of trap it becomes very non-trivial. Now most of the times in physics, what we see that when you try to solve some exactly solvable systems in a standard quantum mechanics book, say infinite square well, hydrogen atom, harmonic oscillators. So what we normally do, we take some kind of answers in the beginning that I predict that kind of solution should fit the system, but here it is not possible because this is a nonlinear system and the solutions are completely unpredictable. So as you know that in literature, new solutions are coming, new kind of excitations are coming. So we do not know what kind of solution it can support. So the trick was, this is actually the loss gain term. I have written somewhere here, loss or gain. So if it is imaginary, if you take the, here it will come without imaginary. So if you take a mod square, that will not vanish. Okay, so if you would give a particular form of loss gain, that will reflect in the solution. Okay, but here it is kept in general because so that you can take some particular thing depending on the situation. So the trick was that instead of taking a particular answer, we take a very general solution, very general trial solution, which has no prior assumptions. So you have a very general amplitude and then some function phi. I'm expecting that the density part will come out. So I do not know whether it will be a function of x and t. So I put some scaled variable of x. You see that if it is naturally coming out as x, that is fine also. But otherwise, you'll have a scaled variable of x and t, which will actually give you the density, and then you have a phase and loss gain term. So if you take this, so far we do not have any information about the system. So you'll have a set of consistency equations. And why consistency? Because they have to be solved simultaneously. If all of them are solved simultaneously, most of them are second order, first order differential equations. And then only it has also a nonlinear equations, which is not mentioned here. I'll mention afterwards. So and solving all of them with a given physical situation is the difficult part. So what we have mentioned in this paper, that there can be some unified approach for such systems, and you can actually handle a couple of potentials together in the same model. So there's no model which can handle more than one potential. Even for harmonic potential in nonlinear system, it is very difficult. So this was a unified model which you have addressed. And so this is one good example that a tunable double well potential, which that it is very useful for quantum information science. And a tunable double well can be handled exactly. So the solutions are exact analytical solutions. And someone can go to the paper and if interested for looking at the mathematics, there's a lot of mathematics in that. And this is in line of the methods which we have given in the other paper. So you can actually tune the well depth and the height, everything, and then you can get the particular kind of solitary configurations. Now coming back to the simulation part, which actually is for bichromatic lattice to start with. However, the optical lattice is very known to all of us now, and it is a periodic structure which is formed of a standing wave of counter-propagating lasers. Now, what is bichromatic lattice is, you have a long wave and short wave, or both of them together, and if you superpose, you will have another minima in between, and in literature it is called a frustrated minima. Now, this kind of potentials are hugely used in literature and in different kind of systems, condensed matter systems, say starting from graphene, twisted graphene, and then Kagam lattice, ratchet potentials, and a lot more. So, we have actually started with this, and this particular phenomenon, which is Anderson-like localization. So it's a beautiful example of quantum simulation. Was reported in 2008 experiment in a quasi 1D BEC. So we started looking at it with this potential at hand, and then what we get is this, that look at yeah.
When you show that frustrated,
yeah.
In which sense it is frustrated?
Yeah. So
you have a deep well, so
yeah. So you can say that it is a periodic, biperiodic, you can say, but in literature, a couple of times in the first few papers, they call it as a frustrated, because the potentials are actually, it was periodic, now it is disturbed from the periodicity, normal periodicity. So in that sense, they call it frustrated, but this is not the frustrated the way it was known in the literature. Yeah, I agree.
So,
yeah.
So in the traditional optical lattice,
yeah,
the lattice spacing is lambda by 2, the counter propagate.
Right.
But for this one, bichromatic optical lattice,
yeah,
what would be the lattice spacing?
Yeah, so you see that this is, imagine a two-dimensional array. I don't have any slide to show you that how it is actually mimicking the condensed matter system. If you have, lattice in 2 dimension or 3 dimension, you take a projection, okay? Because it is 1D, you have to take 1D projection, 1D line, and then the atoms will be like, these are the positions for the similar atoms, and there are different atoms here, okay? So it will show a different potentials. Okay, and that kind of thing it is reflected here. Okay. Okay. So let me go ahead. So what I wanted to point out here, although it looks rigorously mathematical expressions, but starting from the fundamental dynamical equation touching to the experiment is very difficult, because getting solution is okay, but then after that, to addressing a physical system and a particular need is very difficult. So don't worry, this will definitely connect to something which I have expected. So here Cn is a elliptic function, is a modulus parameter. So for localized one, the m should be 1, and then you have a sec hyperbolic kind of profile with a scale coordinate, okay, which I started with in the beginning. And this is an attractive interaction, this is for repulsive interaction. So here I'll get a bright excitation, which you call a bright soliton, and in this case I will get a dark soliton. Okay. So this we have given this model in 2014. So, and also the tunability, you see that to get this kind of solitonic configuration in the experiment is extremely difficult, because when somebody does the experiment, take some initial parameters, but then they're ending up with some solution, but that may not be soliton. So if someone maintains this kind of laser parameters like laser periodicity and the intensity in between, then there are high chance that one can get a bright soliton dark soliton in a way we are expecting. Because if you look at the mechanical system, soliton is a excitations in nonlinear systems. If you see water tank experiment, so they do it, give the excitations many times. There are videos in YouTube, and then there are chances that out of 10 you are getting say 3 times, 4 times. So it depends that if you fix up the initial situation properly, there are very high chance that you will be getting this kind of stable excitation. So here it is that when the lattice depth is very small, so we have taken the parameters from the paper I have mentioned, and then you have a bright soliton, but this BEC cannot see the potential. So it is almost without a potential. But if I increase the height of the laser, like the intensity of the laser, then it starts seeing the the minimum of the potentials, and the accumulation of atoms are probabilities more wherever you have minima. And then interestingly, if you increase it more, there are these so-called frustrated positions appear, and then at some point you'll see that the density will suddenly jump to the central part. That's the surprising effect which we observe here. And if you increase it more, it will be just like a delta function. So I have not increased further because then I cannot plot it. So it will be just a line. So it is a strong localization which we have pointed out in this experiment. And we have confirmed it by condensate fraction and energy calculation and also stability. And this was the article of the year in Laser Physics Letters. Okay, so now this system is much more rigorous. It is the recent work, and what people do is they do a rigorous trap engineering, and the form of lattice, which is our arbitrary shape, okay, and which cannot be formed by 2 frequencies. In 2 frequencies, you can either have this frustration, or else you can have double well super lattice. So you have series of double wells. However, if you mix up more number of lattices, then it is possible. Okay, so here it is a 4-color optical lattice. So you have 4 standing waves, and I'll show you that what are the remarkable things coming out. That this is the kind of expressions we take, and so here, if you look at this plot of the potential, so this cross, so there is nothing. So B1, B2 are 2 parameters, and so B1 0 and B2 0. These are BOL, means bichromatic lattice. Only 2 periods of the lattice, 2 standing waves, and this parabola is 3 standing waves. So it's a tricolor optical lattice, and this line is also tricolor. But you see the periodicities are different: L3, L4L, 2L, 3L, 4L, and the junctions are actually having the common frequencies. Okay, so 3L, 4L, 3L, 4L. So like this you have, but we have been talking about FOL. So no FOL is visible here, is because all these white areas are, other than these lines, all these white areas, all parameters will give you FOL. So other than these lines, and so yeah, so this was yeah. So this is the density pattern. If you look at it now, what is very remarkable here? If you see a double well super lattice, now in between the so-called frustrated depths are appearing, and which makes the cloud separated. And that is actually useful in experiments, because if you want to have this coherent cloud to use in quantum information science, you would look for well separated clouds, right? And so this is what kind of thing is suggested. If you create a kind of situation like this, which is not known in the literature, and then you can actually separate out the clouds very nicely, and you can have a double well superlattice. You see there is no frustration in between, the clouds are not separated. So you cannot use much of this thing, but this one will be a pair of Schrodinger cat, or you can also tell that this has a comp state, which is recently reported. So these kind of things can be easily modeled with this kind of thing. But if you look at the other domain of this, which is a negative parameter of the lattice, then you get an odd number of things. And if you have a well localized, want to have a very well localized cloud, and also kind of a pair of things with a super lattice, then you get the odd number of condensate cloud of this kind. So these are of solitary waves. They're very stable. Yeah. So we have checked the stability for all these parameters. We have taken some particular one, then evolved it with a very large amount of noise. Here it is 5%, 7%, up to 10%. It is very stable. And one thing is important in the bottom figure is that normally the stability is in theoretical studies, also in numerical studies. People do a stability analysis by perturbing the density, the wave function. Okay, but then if you use a laser, if you use experimental setups, there will be also noise, so which is actually creating the potential. So there can be noise in the potential itself. So we address both of them. So the stability due to the noise in the potential is called the structural stability, and this is actually given. This is a standard deviation for potential, and the standard deviation for the wave function. You see that is not much deviated for this in presence of noise. Okay. Now is a different domain that we are very familiar about, positive temperature domain. And this is a negative absolute temperature. It was a very well-known concept in statistical physics that, if you have, say, Boltzmann distributions or B distribution, so if you increase the energy, the number of atoms will become less in number, right? And what about the situation when you have a situation like this, that you increase the energy and the number of atoms also increase? Okay, so this is the normal situation which you see in all physical systems, and this kind of thing requires an upper bound in energy. So you have any potentials, your energy is lower bound, so you cannot go beyond this. If you can have an upper bound in energy, that's the situation you have to look for, and it's very difficult to get in any physical system. So ultracold atom, being a very tunable one, is the first system where it was realized in 2013. That experimentally you can see that this is the way it is done, and the kind of trap it is used is the inverted trap. So normally inverted trap is unstable, but because the atoms are attracting, they are using an attractive domain, is the attractive superfluid, and then you have optical lattice. Okay, so this is the situation which was actually used for negative temperature. And if you look at the momentum space, it is the normal situation of BC, as I said in the beginning, that it is centered in this the momentum space, but in the negative domain it is not. So at the center there is no atom, but then you have the atoms in the higher momentum states. Okay, so now the thing is, from the previous experience, we have seen that this bichromatic part, the frustrated optical depth, which actually helps us to localize the atom. And in negative temperature domain, we always look for the localization. So the more stability you get, system is more favorable for negative absolute temperature. So what is expected is to modify this to a bichromatic part. Okay, although the system will be much more difficult, but then it is favorable because this is not difficult to do in experiment. The same setup of experiment can do that, but this will have a more favorable situations for negative temperature. And we have reported this in scientific reports without publication fee. Okay, so yeah, so this is I will not get into this. So let me just show you the dynamics, how it happens. Now we have also used a tilted trap to incorporate interval kind of the tunneling of atoms, so which is also called the atom distillations, which is observed in experiments in different situations. So here if you see that atoms are kind of tunneling from this thing, but they are not going away. Although you have an expulsive scenario, it is not going away from the trap. Okay, so now the thing is that is a one situation which is giving you negative absolute temperature, but can there be can you correlate with the trap parameters? That is much more important. That if you want to have a kind of a technology in negative temperature, you have to know that how this negative temperature situation can be correlated with trap engineering. So that's what our recent work was. So we have actually this is a shape parameter which we define, and then with that you can see that is a kind of a situation which was taken in the experiment, and then you can also introduce this thing, and then finally you can. So you can take different values of the parameter, and basically the lattice and the expansive trap, which is inverted harmonic, and then you can actually have you can study the system. So we have actually given. Yeah, sure.
So what is beta here?
Just a second. Is it the time remaining? Yes. Yeah. Yes, please.
What is
Yeah, beta is the intensity of the laser. So it is related to intensity, but in the intensity both beta and L are there. Okay, so that's the thing. And L is the periodicity. So these are the main prime factors. So that's why we are starting for that. And omega is the parameter for the inverted lattice, inverted trap. So expansive trap. So now this Donut-Chet condensation fractions, the more yellow area is for the atoms which are the central minima, central bound state. And this one, the blue color is actually the neighboring, the first neighboring site, and the rest of the thing is given by the brown. So you can see that if you increase beta, then you have more localizations. So we will be expecting that more negative temperature. So it's a stable temperature as a quicker negative temperature for larger beta. And with respect to omega, is if you make a more expansive trap, naturally it will be tending to go out. So that's why it is naturally reflecting in condensate fraction. But this is not very easy to understand that if you use a lower value of the period, long lattice, that is favorable for this temperature. Now this is also very interesting that in the literature it is mentioned that if you have a standard deviation more, is a stability more, so it will be naturally having a more favorable situation for negative absolute temperature. Now look at it here, that this is beta and this is omega, and if you increase beta, so it is actually getting less standard deviation, that means is more stable, so that is expected. But here if you look at this axis, if you increase this thing, so it is actually the standard deviation is minus 0.4. We increase, so it is reducing. It is because if you stretch it, say imagine that you have a string and you are stretching it like this, so you are making it more expansive. By making it, you are also changing the depth, and that is actually affecting it and making it more stable. So unless you kind of investigate this, it is not very clear from the primary equations. And we have given also kind of variations of this with different parameters. Minus t, y-axis is minus t, is a log, but this is a normal scale, and this is how it is. So this is recently reported. Now let us talk about a few things in quantum informations. I have a very less time, but excuse me if I exceed a couple of minutes, 2, 3, 5 minutes. So here we have proposed this phenomenon for the first time for BEC, which is fractional variables. It's a very interesting phenomenon. It is observed normally in nonlinear systems, optical fiber, molecule, and so on. So what happens that if you have one cloud, you will have the situation. So we have been using a circular trap, just like a ring waveguide, and then you have a multiple of them. So can we create such situation? That's the question. So imagine that this is a t equals to 0, and then as you propagate to t equals to 1, so is a revival time. The cloud will be reviving at this time. However, the fraction of that, it will be splitted. So without studying this phenomenon, you can predict that how many times it will be splitted in. So at 1/8, it will be split in 4. So that's very well known in the literature. And in half, it will not split, it will go to the other side. So there will be a pi phase difference of this. And if it is an odd number, so there will be rational numbers always. If it is even, it is half of that. I know. So, yeah. So if it is a rational number, odd number, so it will be split in 5 parts. So let me just quickly go on with this. So there are many experiments in the circular waveguide, but nobody has looked at this thing, although they have observed a persistent flow of cloud, but they have not noticed this phenomena probably. And we are actually making this trap in this way. There is so ring trap is a kind of if you rotate a double well, it will become a ring. So this pink ring is formed because of the rotation of this double well, and this is the radius of the ring. Now it is very tricky to make this kind of trap to have a stable condensate. So if you want to have with this many bifurcations, you have to prepare the trap properly. I do not know how they are prepared in experiment because those are not disclosed in the paper. But what we think that you have to model in such a way. So imagine that this is a harmonic and Gaussian, is a combination of harmonic and Gaussian trap. And you have to tune in such a manner that this will map to a harmonic trap. So each well has to be mapped with a harmonic trap. And why so? Because the BEC is formed in the ground state, remember, and you'll be working with the Gaussian function. And that Gaussian function, the BEC has the ground state which is Gaussian. So you have to map the parameter with this Gaussian with the ground state of the BEC Gaussian. And then only you get a stable solution. If you don't match the parameter to start with, you'll not get fractionally reliable. So in experiment also one has to do this. So we have done with the parameters, experimental parameters. And this is typically what we have taken. So this is the initial cloud, okay? And this is the trap which you have taken. And I'll just directly going to the snaps of density. So these are, I think revival time is 2 seconds around, which is quite accessible in experiments. I think the stability one can get in that kind of parameter is around 8 to 10 seconds. So so these are 1, 2, 3, 4, 5, 6. So I can say this is 1/12 of the revival time. So like that you can predict all the times. And we marginally missed these two published in TRL. They said that there is another paper coming in physical review research parallelly. So that's what editor pointed out. But this was a new phenomenon in this system, and they transferred to physical review. Can I run this? I don't know. Is it going? No, it will not, because I have transferred the file and the movie is not there. So anyway, so I wanted to show that how it is formed. But anyway, so this is, I have already showed the snaps, and you can see some experiment which is giving this interference when they're merging it. And these are some articulations where I can exactly say that where how many splits it will happen, and we theoretically model this. So theoretically model this by modeling the cloud and the dynamics. Okay, so let me go ahead. I'll skip this. Okay, so here actually we are doing this part which is interference, and just one slide for quantum sensing. That this is a sensing for tunneling and reflections of BEC, and so using that, this is just communicated. These are atomic beam splitters, and if you just tune the atomic beam splitters, you can get structures which are useful for quantum metrology. And we are predicting indirect measurements of temperature, which is of sensitivity to picokelvin, and from this, so indirect measurement of temperature. Yeah. So this is another work where solitary trains, the experiment of solitary trains were taken with this parameter, then weak measurements were done. So these are meter shift, you can see. So very closer clouds can be distinguished by the meter shift. And this is another one. And here I'm just mentioning that, because as we discussed in the discussion forum, that, I'll be mentioning what are the other things we have been doing. We are also doing rogue waves, scalar vector BECs, a couple of applications of both of them, and then couple optical lattice, which is a very interesting new kind of, is entangled, I can say, we are trying to figure out. So Faraday pattern to distinguish the non-linearity in BEC. And there is a twin Schrodinger cat, which is ACU11 dynamical symmetry. And there's a model for cavity QED for entangled Schrodinger cat, which can give you a very sensitive structure, and also is a very good for decoherence. We have this model, exact model with two cavity system. And dynamical condensation of photons. This is again new directions. So we are proposing something new. And non-diffracting beams with SPDC. So mainly we are emphasizing on array beams. And quantum machine learning, we are actually not doing the machine learning, so-called machine learning. We are predicting algorithms for image classifications with optical setups, like you can form optical gates and entangled states. You can use entangled states and optical quantum circuits to devise a kind of algorithm which can actually have efficient image classifications. So this is another way, another thing that diatomic molecule we are working on one or two problems. So so these are the themes I have underlined. So these are my graduate students. Raghav is here, and MSc project students. I have to thank all of them because most of them are involved in all of this till my last slide. So I thank you very much and sorry for exceeding this time.
Thank you very much, Utpal. Very nice talk and a lot of works.
Yeah, so you had a plot basically saying that the width of these localized states as a proxy for dynamical stability. I was wondering if that correlates very well with, for the Gross-Pitaevsky, you can do a dynamical stability analysis by linearizing fluctuations and so on.
Yeah.
So does this always correlate very well? Because in principle, it depends on the potential and it depends on the grounds or whatever state you're perturbing with respect to. But the width seems like a rather simplistic measure of dynamical stability, no?
With of what?
You had like standard deviation of the cloud size or something, and you said that this is...
No, this standard deviation is the error.
Error in what?
Error is like, say in a given X, so I take some particular value of X, some micrometer, okay? And then you see the amplitude in the density, so probability actually. So time evolved density and the evolved density after adding the noise.
Okay.
So is a standard deviation between these two.
I see.
Each and every points we had to measure this standard deviation.
I see. Okay. Sorry.
Yeah. So that's why you have seen that, the throughout the axis, it was wrong. Yeah. So that one can see that what the error is actually coming.
So if there is no more question, let us thank the speaker.